Welcome to a presentation about FEKO, the Comprehensive Electromagnetic Field Solver. This presentation forms part of the Altair HyperWorks webinar series. The HyperWorks Partner Alliance offers customers with on-demand access to applications that complement Altair's suite of applications. FEKO provides the solution for electromagnetic field analysis. What is computational electromagnetics? Maxwell's equations describe electromagnetic field phenomena, and CEM, or computational electromagnetics, is the numerical solution of Maxwell's equations for different problems. CEM has become an indispensable tool for the design and analysis of devices and systems where electromagnetic fields are present. If we plot the different applications on a map, where the horizontal axis represents the complexity of the structure and the materials, and the vertical axis, the electrical size of the structures that are solved, a map will look something like this. For example, at the bottom left, there is a resonant wire and an antenna, and at the bottom right, there is a human head with many different dielectrics. In the top left-hand corner, we have the upper deck of a ship at radar frequencies. No single CEM solver is able to solve all these problems. Different solvers are optimized for different applications. For example, the finite element method and the method of moments are used for geometrically complex structures which are electrically not too big. The MLFMM is a special solution of the method of moments and is applicable to complex structures which are electrically big. At even higher frequencies or electrically large structures, asymptotic techniques such as the physical optics or the geometrical optics and the uniform theory of diffraction is required. In FEKO, these techniques have been hybridized to solve large and complex problems simultaneously. We will now look at the use of FEKO in different industry sectors. The following main industry sectors have been identified: automotive, aerospace, naval, RF components, antenna design, mobile phones, bioelectromagnetics, integrated wireless devices, and the general communications industry. Here's a selection of our customers. For example, in the aerospace and the defense, you can see EADS, European Space Agency, Boeing, Northrop Grumman, and for the automobile, there's, for example, BMW, Bosch, Daimler, Nissan, and Peugeot Citroën. Let's have a closer look at the aerospace industry. For the aerospace, antenna design and placement are particularly important. Antennas are normally designed and specified as if they are mounted on a simple ground plane, as shown here. The radiation pattern, as simulated with FEKO, is very similar to antenna test data. However, when the antenna is placed on a platform, the radiation pattern will change. In this case, the antenna is located below the aircraft, and the resulting radiation pattern can be seen here. This solution was obtained with the physical optics technique. In this example, a microstrip antenna was first designed, and then the effect that the missile has on the performance of the antenna was determined. The antenna is solved using the finite element method, and the missile is solved using the MLFMM technique. The first step is to design the antenna on its own. Two techniques were used: the finite element method and the method of moments for the planar Green's function. We can see in this graph that the results for the finite element solution and the method of moments agree very well. The next step is to see what the effect of curvature has on the radiation pattern of the antenna. The conformal antenna was used using the finite element technique, and in this case the finite element technique is also used for the planar antenna. This figure shows that the radiation pattern was not changed significantly by the curvature of the antenna. The next step in solving the problem is to mount the antenna on the missile. It is clear that in the main beam the radiation pattern is not changed significantly, and the performance of the antenna will not be affected too much. In another case study, we look at the design and analysis of an antenna array for a satellite. The Iridium satellite system is used for global mobile communications and consists of 66 satellites with spot beams covering the whole surface of the Earth. The ground coverage antenna consists of 106 circularly polarized patch antennas forming an array. The first step would be to design the single element antenna. The typical parameters of interest would be the input impedance, the axial ratio, and the gain. After the design of the single element has been optimized, we can move on to the design of the array. Because of the electrical size of the array, the MLFMM technique is used. The standard method of moments would require 53 gigabytes of memory, whereas the MLFMM requires only 2.8 gigabytes. The left-hand circularly polarized gain and the right-hand circularly polarized gain is calculated. The axial ratio can also be displayed for the different angles. Now that the antenna array has been completely characterized, the influence of the satellite can be determined. The MLFMM technique is again required to solve this big problem. Shown on the left is the electrical surface currents. On the right is the radiation pattern of the complete assembly. The analysis shows that the satellite body has very little effect on both the right-hand circularly and the left-hand circularly gain in the direction of the main beam. Because of the multitude of antennas often used on ships, the naval environment poses a real challenge to EM solvers. A typical design problem is the antenna layout on the upper deck of a ship, where radiation patterns, inter-antenna coupling, and radiation hazards needs to be considered. Shown here are the radiation patterns for two positions and two different orientations of a disc cone antenna. It is clear that there is a change in the radiation pattern depending on the antenna position. CEM tools are increasingly used in the automotive industry, from antenna design and integration to electromagnetic compatibility analysis. One of the first challenges is to create a suitable mesh. The CAD models that are most often obtained from mechanical CAD packages usually contain too much detail. The first task is to fix such models and retain only what is required for the EM simulation. For example, decisions have to be made regarding the inclusion and handling of transition resistances at hinges, a real ground, where the wheels and the plastic or the windows should be included in the model. Shown here are the electrical surface currents around an FM antenna that is located inside the fender above the rear wheel. A comparison between the measured and the simulation radiation patterns show an excellent agreement. FEKO has been used for the design and analysis of tire pressure monitors. Here, the field strength is calculated for different positions. In this case, FEKO was used to design and integrate a CB antenna for a truck. The antenna will be mounted in the rear view mirror. The first step would be the design of the antenna on its own. The operating frequency is 27 MHz, and the antenna is etched on a thin film. Once the antenna has been designed, it can be integrated into the rear view mirror, and the radiation pattern of the antenna plus the truck cab can be simulated. The theta and the phi components of the radiation pattern is shown here. The next step would be to see what effect, if any, the trailer has on the performance of the antenna. You can see that there's a relatively small change in the radiation pattern. It has become common practice to integrate antennas into the windshields of vehicles. These antennas include TV, FM, GSM, and GPS antennas. It is, however, too complex to do a full 3D analysis of the thin layers in the glass, and special formulations have been developed to solve these. The solution caters for the multiple layers, the curvature of the windscreen, and the car body. The formulation used in FEKO is based on the method of moments, and only the metallic elements are meshed. Full consideration is given to the boundaries between the dielectric layers and the coupling between closely spaced antenna elements, the finite size of the windshield, the curvature of the windshield, and we can have multiple windscreens. Shown here is a validation study that was done. Two simulation methods and measurements are compared. The S11, or the impedance match, shows an excellent correlation between both simulation methods and the measurements. For the complex real-world case, there is also excellent agreement for the antenna reflection coefficient. Now we will have a look at other applications for FEKO. These include bioelectromagnetics, antenna design, antenna placement, RF component design, scattering analysis, and EMC analysis. FEKO can solve a very broad range of antennas. These include wire antennas, horn antennas, planar microstrip, large arrays, conformal antennas, broadband, and reflector antennas. Here is an example of a broadband antenna that was designed and made at the University of Colorado in Boulder. Some of the variables in this case are the number of turns and also the height or the pitch of the antenna. A comparison between FEKO and HFSS shows excellent agreement for the impedance. The same is true for the axial ratio. And a comparison between the measured and the simulated axial ratio also shows excellent agreement. A cross-sectional view of the E-fields show how the active part of the antenna is changed for the different frequency bands. FEKO can be used to design the RFID tags, their application, and the design and placement of the RFID reader antenna. RFID tags operate at around 900 MHz, are very cheap, and are often printed on a flexible substrate. Some of the deployment considerations are the effect of bending of the antenna, the effect of the tagged item on the performance of the tag, and for the reader antenna, the placement might need to be considered. For this Excalibur antenna, it was found that the effect of bending is negligible, and if placed on a plastic soft drink bottle, the distortion is also not too severe. However, if the tag is placed close to metallic structures, the pattern is changed significantly. If you look at the tag reader antenna, it can be designed in isolation, or we can solve it where it's integrated with, for example, a forklift, and if required we can look at the total environment, in this case the warehouse. CEM codes are also used to analyze the interaction between electromagnetic waves and biological tissue. The fields inside the head of a mobile phone user can be calculated, and the specific absorption rate, in watts per kilogram, can be calculated inside a 10 grams cube, according to international standards. The hand and its position around a mobile phone can change its reception quality. From these images it is clear that the pattern of a PIFA antenna can be changed significantly if the hand covers the antenna. More complex scenarios, where the environment surrounding the human is taken into account, can also be modeled. The hybrid MOM-FEM formulation is specifically useful for this application. The MOM is applied to the antenna or the vehicle, and the finite element to the human phantoms. In this study we looked at the safety surrounding the TETRA radio system, where the antennas can, for example, be mounted on a motorcycle, or where the radio is worn on the chest, or inside a confined space, such as a vehicle. The study of electromagnetic compatibility covers a very broad range of problems. These include cable coupling, antenna coupling, radiation hazard zone analysis, shielding, susceptibility, reverberation chamber analysis, TEM cell analysis, current injection, and conducted emission. It is sometimes required to simulate the whole EMC measurement setup. In this, the car or the device under test, the rotating ground plane, and the EMC test antenna are included to determine the field distribution inside the vehicle. Electrical cars are becoming more and more popular. One of the challenges facing this industry is coupling between cable bundles, which in turn lead to the interference between different systems. This, for example, can be between a cable carrying high current for the transmission motors and a low power data cable. The new combined method of moments and transmission line method allows the analysis of complex cable bundles which are shielded and can have an arbitrary path inside the vehicle. The next application is scattering analysis. Due to the accurate MLFMM and the asymptotic high-frequency techniques, FEKO is very suitable for the analysis of large scattering problems. Shown here are some validation simulations that have been done. As an example, we will look at the monostatic RCS from a military aircraft at 1 GHz. The accurate MLFMM solution is used as a reference. It is found that where there are no multiple reflections caused by the target, the ray launching geometrical optics techniques and the PO give good results. However, when the structure does support multiple reflections, for example, at the cavity at the inlet of the engine or between the wings and the body, these multiple reflections need to be taken into account by using the ray launching GEO. FEKO allows the analysis of composite materials. The fiber properties and the direction can be specified for each layer. In this simple example, it can be seen that the electrical surface current and the resulting scattering can be very different for a metallic and a composite structure with the same shape. Passive waveguide components and microstrip circuits form a very important part of computational electromagnetic analysis. Shown here are two coupled spiral resonator filters and a tunable comb line filter. And these are typical parameters that are obtained from such analysis. Waveguide ports, desired modes, and the output parameters, for example, S parameters and near fields, can be specified very easily in CAD FEKO. This shows the near fields inside a Magic T waveguide coupler, where the sigma port excitation splits the power in phase between port 3 and port 4. When the delta port is fed, the power is split between port 3 and port 4, but with 180 degree out of phase. To conclude this presentation, we will look at the major components of the FEKO suite. The GUI consists of 3 programs. CAD FEKO is used to define the geometry, specify the excitations, select the solution techniques, and define the desired output. Edit FEKO is a scripting interface for advanced users, and Post FEKO is used for the post-processing of the simulation results. There are 3 main methods to obtain the CAD geometry for analysis. Firstly, FEKO has its own parasolid-based CAD interface in which primitive objects and Boolean operations can be used to define parametric geometry. The second way is to import geometry from third-party products. These include ACES, CATIA, IGES, and ProEngineer. And lastly, a mesh can be imported and manipulated further for analysis. Some of the mesh formats that are supported are Abacus, ANSYS CDB, Nastran, Patran, and STL. PostFEKO supports multiple models and the associated data simultaneously. Multiple windows can be opened for different data sets, and 2D and 3D visualization of electrical currents, electric and magnetic fields, radiation patterns, impedance, and S parameters can be obtained. Many advanced features are available. For example, cut planes, isosurfaces, contours, SAR extraction, and image and data export. Lastly, FEKO has a well-established sales and technical support network. You are most welcome to contact us if you need more information. Thank you.